Welcome back to CSE 201. I hope you guys are all healthy during this special time. And if you have anything that I need to know and that may influence your study, please let me know as soon as possible. Since healthy is more important than the study. In last week's class, we have learned the classical crypto systems, DS, AES, triple DS, RSA, and elliptic curve. So let's have a simple review of that. We have talked about symmetric encryption and asymmetric encryption. You should know that DS, AES, triple DS, they are symmetric encryption since they use the same secret key for encryption and decryption. RSA and elliptic curve, they are asymmetric encryption. A pair of keys got generated, and one of the key pair is used for encryption, and the other one is used for decryption. Also, that you should know that the DS is not secure anymore, so you should not use it anymore. And symmetric encryption method is much faster than the asymmetric encryption. In real world applications, even our RSA, elliptic curve, these asymmetric encryption are still safe to use, but they use more computation resources and they are much slower than symmetric encryption. So asymmetric encryption is firstly used to establish the secret key, which means exchange the secret key between the parties, between Alice and Bob in our example. Then the exchange the secret key, which was the plain text of the asymmetric encryption, now is available to use in the symmetric encryption. For example, we can use Diffie-Hellman key exchange protocol or RSA to exchange the secret key of AES. Then after the exchange, we can use the AES or triple DS to encrypt the following communications between the parties. In today's lecture, we have two main things to talk about. The first is called mode of operation. The other one is hash function. So hash function and mode of operation. Mode operation is located a little bit inside the encryption method. It describes how to repeatedly apply a cipher's operation to securely transform amounts of data larger than a block. In cryptography, a block cipher mode of operation is an algorithm that uses a block cipher to provide information security, such as confidentiality. A block cipher by itself is only suitable for the secure cryptographic transformation of one fixed length group of bits called a block. A mode of operation describes how to repeatedly apply a cipher's single block operation to securely transform amounts of data larger than a block. A block cipher takes a block of plain text bits and it generates a block of ciphertext bits, generally of same size. The size of block is fixed in a given scheme. The choice of block size does not directly affect to the strength of encryption method. The strength of cipher depends upon the key length. AES, DS, RSA, they are all block ciphers. The block size of AES is 128 bit. So for AES, the block size is 128 bits, and the block size of DS is 64 bits, and some block ciphers support a variable block size. The opposite of block cipher is called stream cipher. So a stream cipher is a symmetric key cipher where plaintext digits are combined with a pseudo-random cipher digit string. In a stream cipher, each plaintext digit is encrypted one at a time with the corresponding digit of the key string to give a digit of the ciphertext string. The pseudo-random key string is typically generated serially from a random seed of value using digit shifted registers. The seed value serves as the cryptography key for decrypting the cipher's text string. Stream ciphers represent a different approach to symmetric encryption from block ciphers. Block ciphers operate on large blocks of digits with a fixed, unvarying transformation. In block cipher, block encryption methods, no matter how large a block is, uh, let's say like 1 million bits, the plain text is still possible larger than the block size. So the size of plain text under like any circumstance, uh, it is possible or very possible larger than the size of the block defined in the encryption methods. So we need to define how to deal with the part outside one block. For example, the block size of the encryption method we're using to encrypt it is 100 words. So we use the unit of the words, not the bits, not the bytes. Okay, but the total number of the words of one article is 654 words. So how do we cut the article and how do we pay the left 54 words is the responsibility of mode of operation. As to there are two very important conception. One is the initialization vector called IV, and the other one is padding. We will describe them later in a real example. And these are the common mods. Different cipher mods mask patterns by cascading outputs from the cipher block or other globally deterministic variables into the subsequent cipher block. The simplest of the cipher mods is the ECB, which is electronic codebook. But it has a very serious security issue, so do not use it. And we will see the reason later. Then it's the CBC, the cipher block chaining. CBC was invented in 1976. In CBC mod, each block of plain text is XORed with the previous cipher block before being encrypted. This way, each ciphertext block depends on all plaintext blocks processed up to that point. To make each message unique, an initialization vector must be used in the first block. The rest three, CFB, which is cipher feedback, OFB, output feedback, and the CTR, which is counter. We're not gonna learn them. You just need to be familiar with those names. That there are many modes of operations can be used right now. Typically, we can say we use the AES to encrypt something, we use the DS to encrypt something. But since mode of operation is part of the encryption, so there is a longer name, or say full name, for the entire encryption. So let's see one example. So how to interpret one AES 128 CBC. So uh, in the first part, the ES 128 means the encryption method or the cipher, and its block size. Since AES has three different options for the block size, one option is 128 bits, then 192 bits, or 256 bits. So here we use the AES 128 means the block size is 128 bits. And the CBC means the mode of operation is the cipher block chaining. Okay, so this is the full name of the uh, block cipher. And so how about this one? And the DS-CFB. So you may have one question that since we use the AES 128 to represent the encryption method and the block size, why do we write the same thing like the DS 128 CFB? So the reason is that there is only one option for the DS encryption method, is the block size. So the 56 bits is the only one option for the block size. So you can just emit the 56 after that. So there is no DS 128 CFB. Let's see the first mod operation we're going to describe today, the ECB, the electronic code book. So the entire message is divided into 64-bit or 128-bit blocks, which means the blocks of the entire plain text can be, say, the 64 bits or the 128 bits. So this is the whole plain text, and each one is one block. It may 64 bits or 128 bits. Then each block is processed independently, separately. So this one must be processed independently, same as this one, same as this one. So a powerful computer can separate the whole plain text and process them, all of them at the same time. So that there is no relationship between the encryption of this block and the encryption of this block. But there is one problem. So if we have the identical content in the block 2 and block 3, so they will lead to the same cipher text block. So this is the one of the security issue. So this is the one example that how to do the encryption under the ECB. So we can see the plain text can be divided into several blocks, and each block has the same size except for the last one, because the total length of the plain text may not be the multiple of 64 bits or 128 bits. So at this time, we can just pad the last block, do the padding for last one. Then we can do the encryption, and there were three advantages for the ECB. First one, we can do the encryption in the parallel manner. So the second one is very similar. We can also do the decryption in a parallel manner. And the third one, we can do the random access. Since there is no relationship between the ciphertext of the first block or the second block or a third block, so they are totally separated. So there is no relationship between them. And for the decryption, it's the same thing, and no relationship between the different blocks of the ciphertext. So no relationship between the different plain text of the decrypted plain text. So we can do the decryption for the different blocks separately, then concat them together as the final plain text. This is what I mentioned, the serious security issue of the ECB. The disadvantage of the ECB is a lack of diffusion, because ECB encrypts identical plain text blocks into identical ciphertext blocks. It does not hide data patterns well. ECB so is not recommended for use. A striking example of the degree to which ECB can leave plain text patterns in the ciphertext can be seen in these two figures. When ECB mod is used to encrypt a bitmap image, which uses large areas of uniform color, while the color of each individual pixel is encrypted, but the overall image may still be discerned, as the pattern of identically colored pixels in the original remains in the encrypted version. So the left one is the plain text. So the thing I wanted to mention is that the plain text may not always be text. So it can be files, it can be image, because so everything in your computer can named as a file, and they can be written into some characters, which is text. So we can call those images videos, voices, and the texts as plain text. So in the plain text, we can see this penguin, and in the ciphertext, we can still see the pattern of the plain text, and that it is one penguin, not anything else. Let me explain what a bitmap image is, so you may understand the reason behind this transformation. A bitmap describes a type of image that web users encounter all the time without realizing it. Basically, it is a grid where each individual square is a pixel that contains color information. The key characteristics are the numbers of pixels and the amount of information in each grid square, which is one pixel. These are the common file formats of the bitmaps, like the BMP, GIF, JPEG, EXIF, which is very common in the digital camera, the PNG, which supports the transparent feature, and the TIFF, and there is one very new format called WebP, which is developed by Google. Bitmap is not like the vectors. If you enlarge one bitmap, you may find it becomes unclear. So let's see this cat image here. If you just enlarge this part, you may find that there are so many blocks here. So one block here is 1 pixels, and there is no color transition inside 1 pixels. And let's see this one. The color of one pixels can be represented by the color scheme. So the RGB is one of the color scheme we can use to represent the pixels. And if you want the transparent, you can use the RGBA. The A represents the word alpha. And if you work in a printing factory, you may be familiar with the CMYK. So these are the different color scheme to represent the color of the pixels. But let's see this example with RGB. So RGB means red, green, and blue. You have the number from 0 to 255. There were totally 256 possible value candidates for each sections. So we may write the red value is 56, and the green value is 100, and the blue value is 171. So this represents the RGB value for this pixel. Okay. And if you write them in the hex mod, that would be dash 3864, and AB 38 is same as the 56 in the RGB value. So from now on, we can see each pixels or each color can be written as the text. So we can convert one image to all these squares or tables that each one inside is the numbers. So we can convert the image file to texts. Okay, that's why we can use the encryption method to encrypt the image. Let's see the second mode of operation, CBC, cipher block chaining. In CBC, each previous cipher block is chained with current plaintext block. Even identical plaintext blocks will produce different ciphertext as long as their preceding ciphertext blocks are different. In CBC mod, each block of plaintext is XORed with the previous ciphertext block before being encrypted. This way, each ciphertext block depends on all plaintext blocks processed up to that point. To make each message unique, and initialize a vector, which is IV, must be used in the first block. If the first block has index 1, the mathematical formula for CBC encryption is the CI, which presents for the ciphertext of ith block, then is using the encryption method of the PI, which is the ith block of the plaintext, then X or the previous ciphertext block, and then the C0 is the IV. In the figure, we can see the encryption of the first block, and there is one initialization of vector, so the size of the initialized vector should be as same as the size of the plaintext. Then we do the XOR on the plaintext block and the initialization of vector. Then we can get one result. Then we use the secret key to encrypt the temporary result. Then we can get to the first ciphertext block. Then in the second block encryption, we don't use the initialization of vector anymore. We use the first block of the ciphertext instead to do the XOR operation with the second block of the plaintext. Then it's the same thing for the third block. We use the ciphertext block of the second plaintext block to do the XOR operation. Then continue doing this, we can get to the final encryption result. So this is how CPC works. Because of the feature that the same plain text use different ciphertext, the encryption result of this plain text image under the CPC mode of operation, the result will become this ciphertext is totally different with the result of the encryption under ECB, in which we can still see the pattern of the penguin. So in the encryption of the ECB result, so those same color pixels will yield the same encryption result. That's why we can still see the black and white patterns on the ECB encryption result. But since the same plaintext use different ciphertext, we cannot get to the same or even similar ciphertext block under the CPC mode. So that's why we see no patterns in the encryption result under the CPC mode. Before introducing the second part of this lecture, the hash functions. So we need to know why do we need to use the hash functions. So let's see the cryptography applications first. I think you guys still remember the CIA tried the security objectives. Yes, they are confidentiality, integrity, and availability. Confidentiality means no illegal read or unintended privacy disclosure. Integrity means illegal write or program execution. Availability means ensuring legal read, write, and execution. If you look back what we have learned in previous lectures, we know the CIA security objectives, we know those crypto systems. So have you tried to connect them together? So what is the relationship between those security objectives and those crypto systems, those encryption methods? Let's see these simple two security objectives first: confidentiality and integrity. So since confidentiality means no illegal read or unintended privacy disclosure, so if we can use the encryption method, if we can use the ciphers to encrypt the plain text, so no one else can read the ciphertext except for those people who have the secret key. So this can guarantee the confidentiality because there's no one can read it, no illegal read, right? So the encryption method, the ciphers, the crypto systems, they can guarantee the confidentiality. They can provide the confidentiality. So in fact, we often write the symmetrical encryption, but asymmetrical encryption can also provide the confidentiality. As long as it's a secure encryption method, it can provide confidentiality. But the asymmetric encryption is not that often used in encryption because it's much slower than the symmetric encryption. And also the asymmetric encryption has a more important usage during the secure communication. So we often write the symmetric encryption here. But for the second security objective, the integrity, can the encryption provide the integrity? The answer is it is not. So the encryption method only cannot provide the integrity. Even the attacker cannot decrypt the encrypted message. He can just use some other plain text to replace what you really wanted. So the encryption itself cannot guarantee the integrity. So that's why we need a hash function. Hash functions are related to checksums, check digits, fingerprints, or the digital fingerprints, and lossy compression, randomization functions, error correcting codes, and ciphers. Although the concepts overlap to some extent, each one has own uses and requirements and is designed and optimized differently. But in this lecture, we will know the relationship between the hash function and the checksums. So what is hash function? A hash function is any function that can be used to map data of arbitrary size to fixed size value. So notice the definition. It's a mapping relationship between the arbitrary size of data with fixed size of value. Also, we don't talk about the mathematic foundations behind it. We just care about the application of using it. But its general formula is very simple. So we can write a hash function like this. The uppercase h of m equals lowercase h. And the lowercase h, which is the result of the function, is also called the message digest. And the m here, you can call it the plain text. And so the uppercase h, this is the function or hash function. One ideal hash function should has the following properties. The first, it is deterministic. Any copies of same message should always result in the same hash at any time, and it should be quick. It should be very quick to compute. It should be infeasible to generate a message that uses a given hash of value. This means that giving a hash a value, intentionally generate a message for this hash a value should not be possible. Then it should be infeasible to find two different messages with the same hash a value. So any two different messages will yield different hash values. Then a tiny change to the message should change the hash value so extensively that the new hash value appears uncorrelated with the old one. So this is basically the diffusion we have talked about. In generally, there are three properties we need to notice. So the first one is the pre-image resistance. So given a hash value h, it is computationally difficult to find the m such that hm equals to h. This means that we have a hash value, but it should be very difficult to find the plain text that we can compute the hash value of the plain text that is exactly same as the given hash value. And the second property is the second pre-image resistance. So given the M1, the plain text M1, it is computationally difficult to find another message M2 such that they have the same hash values. So this is the one we mentioned that it is infeasible to find two different messages with the same hash values. So any two different messages will yield different hash values. And the third property is collision resistance. It is computationally difficult to find any pair of message M1 and M2 such that the M1 and M2's hash value is the same. This one seems same as the second properties, but in the third property, we have no given plain text, so we need to find one pair of the message. And in the second property, so the one plain text has already given, so we need to find the other one. So these two are different properties. Let's see some famous or common hash function standards. So the first one is called MD5. The full name is Message Digest 5. It is a 128-bit hash function. This means the result of the MD5 is 128 bits, no matter how large is the input. Even you use the MD5 on Blu-ray videos, so the result is still 128 bits. And even if your input is just like a 2-bit, so the result is still 128 bits. Okay, so MD5 is not secure anymore. The word secure here is kind of different between the hash function and the encryption method. So the security of the encryption method may means no one can crack it, but the hash function's security means different things. As long as you can break one of the properties we mentioned in last slides, so it means it's not secure anymore. MD5 got broken in 2004 by Xiaoyun Wang. With the algorithm proposed by her, you can find the collisions in seconds, even on a laptop. You don't need a supercomputer. So just one laptop, you can do this. Then the second standard we need to talk about is SHA-1. The full name is Secure Hash Function 1. It is 160-bit hash function, which means the size of the output is 160 bits. So it is considered insecure also, and it is practically broken in the 2005. But in 2005, there is no actual case that shows the collisions of SHA-1 has already been found. And then the hash function standards are SHA-2 family. The output can be 224, 256, 384, and 512 bits. And the SHA-3 family, so the output can be arbitrary size. In February 23rd, 2017, more than 20 years after the SHA-1 was first introduced, Google announced that the first practical technique for generating a collision for the SHA-1. This represents the culmination of 2 years of research that sprung from a collaboration between the CWI Institute in Amsterdam and Google. As a proof of the attack, they released 2 PDFs. So the left one, this is the first PDF, and this is the second PDF. The 2 PDFs that have identical SHA-1 hashes, but different content. It is so clear that the color here is blue and the color here is red, but they have the same hash value of the SHA-1. Okay. In 2013, Marcus Stevens published a paper that outlined a theoretical approach to create a SHA-1 collision. They started by creating a PDF prefix specifically crafted to allow us to generate 2 documents with arbitrary distinct visual contents, but that would hash to the same SHA-1 digest. In building this theoretical attack in practice, they had to overcome some new challenges. They then leveraged Google's technical expertise and the cloud infrastructure to compute the collision, which is one of the largest computations. Here are some numbers that give a sense of how large scale these computations was. So it's totally 9 quintillion SHA-1 computations is in total. So you may not know this unit, but Let me write this number. Yes, this is quite long. So this is the total computations they need to finish. So if you use one advanced CPU to do the computation, you might need like 6,500 years to finish this. But if you use one advanced GPU to do this, you can finish this within 110 years. And Google, they used many GPUs on these computations, so they can get the result not that quick, but it is much quicker than the 110 years. If you think this is interesting, you can open their website, the Shattered.io, to download those two PDFs and do the SHA-1 computations by yourself. Many operating system websites provide the hash values of the ISO image file. So after you download the file, you can compute the hash value locally, then compare the value with the provided value. So, for example, in this figure, this is the hash value of the Ubuntu 18.04. This kind of computation or verification could make sure the file you downloaded did not got modified during the transmission. So we also call this as a checksum. I strongly recommend you to do this kind of verification after you downloaded the operating system image from internet. Let me tell you a story that why this checksum verification is very important. Some of you may be familiar with this icon, which is the Xcode. Xcode is one IDE developed by Apple, and it can be used to develop the Mac OS app, iOS map, iPad OS app, and some C++ applications. And Xcode Ghost are modified versions of Apple's Xcode development environment that are considered malware. The software first gained widespread attention in September 2015 when a number of apps originating from China harbored the malicious code. It was thought to be the first large-scale attack on Apple's App Store. The problems were first identified by researchers at Alibaba, and over 4,000 apps are infected, according to FireEye, far more than the 25 initial acknowledged by Apple. Xcode Ghost is an example of compiler malware. Instead of trying to create a malicious app and get it approved in App Store, Xcode Ghost creator targeted Apple's legitimate iOS or macOS app development tool, which is Xcode, to distribute the malicious code in legitimate apps. Xcode Ghost creator repackaged Xcode installer with the malicious code and published links to the installer on many popular forums for iOS or macOS developers. Developers were incited into downloading this tempered version of Xcode because it would download much faster in China than the official version of Xcode from Apple's Mac App Store. When the developers installed what they thought was a safe app development tool, they actually got a tempered version that would compile the malicious code alongside their actual app's code. These developers, they don't know their apps had been tempered, so they submit their apps to the App Store for distribution to iOS devices. This sounds very ridiculous, but it is a bad thing that most developers don't have the habit to check the hash value or the checksum of the file they just downloaded. And this is one of the important reason of this Xcode Ghost event. On the right figure, it is one GitHub repository that they provided the SHA-1 checksum that you can use to check to verify if the downloaded Xcode is legitimate or tampered Xcode. So it is the same thing for the other files. Once they provided the checksum, you better do the verification for security reasons. There are many different hash functions, such as MD5, SHA-1, and SHA-256, which is one of the SHA-2 family. And for example, we have a message 1, 2, 3, 4, 5, 6 without the quotations. And the result of the MD5 functions will be like this. And the result after the SHA-1 hashing will be like this. And the output of SHA-256 is like this. Let's see more examples. Even the big video files and image files, they can generate the fixed size hash values. Notice these three sentences here. The first one with uppercase F, and the second one with the lowercase f, and the third one, the letter O has been replaced by the number 0. So this kind of tiny changes in the plain text will yield totally unrelated hash values. So you cannot find the difference between these three hash values. This is one of the features of hash functions. If the hash value of these values are very close, some people think the hash function is not strong enough. Okay, let's see how to apply the hash functions. So for Alice and Bob, so Alice wants to send some data to Bob, but how Bob know the data is not tampered, is the original data? So for this data, we can do the hash functions on the data, and we get the hash values, then concat them together. Then Alice can send these whole things to Bob. After Bob receives these whole things, Bob can separate the data and the hash values. Because the hash function is available for everyone, it can be used by Alice, and it is also can be used by Bob. So Bob can compute the hash values of the data he received and do the comparisons. So if the hash value he computed and the hash value provided by Alice is the same, we can say that the data has not been tampered with. But there is one little tricky here. Let's see the next example. Okay, we noticed that the communication between Alice and Bob, the communication channel is not encrypted. So this means that attacker is possible to capture the data between Alice and Bob. So Alice sent the whole things to Bob, but it was eavesdropped by Darth. And it's the same thing. Darth can also separate these whole things and separate the whole things to data and the hash values. Then Darth can modify the data and append the new hash values. After Bob received these concatenations, Bob will do the verification, and he split the data and the hash values. He do the comparisons, but there is no problem because these hash values is the hash values of the modified data. So this is what we call man in the middle attack, and this is a typo. It is man in the middle. Next, let's see how to solve this problem. This is a diagram for simply applying the hash functions. So the message M and the computed hash values, then concat them together. Then this whole concatenation can send it to the receiver party, and the receiver party can do the verification by computing the hash values. But this one, it is not secure because the man in the middle attack can be deployed on this kind of transmission. So let's see how we can solve this. We can apply encryption on the computed hash values here using the encryption method E with the secret key K. So this is encryption. And then concat the message with the encryption together. So here is not the plain hash of values. This would be the encrypted. This is under the assumption that the send party and the receiver party, they both know the secret key K is known to A and B. And then after B receives this whole concatenation, B can separate the message and the encrypted hash values. So we can do the decryption function here with the secret key K, and B can do the comparison later. The combining of the symmetric encryption and the hash functions can guarantee the integrity. Okay, we finally solved the problems left in the previous slides, that how we can achieve the integrity. Alright, this is almost this lectures. In next lecture, I will show you how to do the encryption, how to do the asymmetric encryption, symmetric encryption, and the hash functions on your computer or on the web browsers. So see you next time.